Hello and welcome back to Anton Math. Now we've been talking about vectors and matrices really just to get an idea of what a matrix is. And in this video we're going to go over how to use a matrix to solve a system of linear equations. Now this is really our goal in terms of matrices, and the idea behind solving this system of linear equations with matrices is going to be key to the next part of the course when we talk about elementary number theory. There are some processes there that are very simplified if we just use a matrix. So this is a very important video I'll be referring to this one a lot in our next part when we do elementary number theory. So let's go ahead and jump in. Now let's consider a system of equations. Now recall that we can write this system of equations as a matrix, or a matrix equation, right? We know that we can write this system of equations from our previous video as the matrix 2, 4, -4, -2, 4, 6. Oops, that's not true. This is a 0 here, 0, -2, 4, 1, -1, 4. And we can multiply that by our variable vector x, y, z. And then we get our solution vector 4, 6, 10. Now if you don't know what I just did there, make sure to go back and watch the video talking about matrices, just the first video about matrices, the introduction. We show how this works out here using dot product, things like that. But this isn't the form of the matrix that we're going to use to solve this system. To solve this system, we're going to use what's called an augmented matrix. So we define an augmented matrix of the system AX equals B to be the matrix AB. We kind of adjoin the solution column B. So really A here is my matrix, X is my variable vector, and B is my solution vector. That's what all of these mean. So we have this system AX equals B is the system of equations, and we define an augmented matrix to be this matrix A. We found our matrix A to be 2, 4, -4, 0, -2, 4, 1, -1, 4. And then we draw a little line here. Some people use a dotted line or a bar, doesn't matter. And we put our solution vector, 4, 6, 10. All right, so we have our matrix with our solutions. Now, really what we should be thinking here is this column represents the x's, this column represents the y's, and this column represents the z's. So what I'm going to talk about next is we can think of it as just doing it to the original system, right? We have the system of equations up here. And what we want to do is we want to reduce this matrix using what we call the elementary row operations. We have 3 elementary row operations. The first one, we can permute the rows of the matrix. So I can take any of these rows and exchange it with any of the other rows. In other words, I can change the order of the rows. My second operation is that I can multiply a row by any non-zero constant. And my third operation is that I can add a multiple of one row to another row. Now, just so there's no confusion, I don't have to multiply the row by anything to add it to another row. Really, I am multiplying it by 1, right? Now what happens when we do any of these operations is if I perform one of these 3 elementary row operations to my augmented matrix, I'm going to get a new augmented matrix, but my new augmented matrix is going to have the same solution set as my original matrix. And when I say solution set, I mean solutions for the variables x, y, and z. Now this should be pretty easy to see that these operations are okay to use, because permuting the rows of a matrix, well, if we just considered the system, that's the same thing as listing the equations in a different order. And of course that doesn't change the solution set for the system, right? I'm just changing the order in which I write the equations in the system. The solutions x, y, and z will be the same. Multiplying a row by a non-zero constant, well, what that's doing up here in my system, I could take, for example, this first equation that corresponds to the first row of my augmented matrix. If I multiply both sides of this equation by 10, I'm still going to have the same solutions for x, y, and z, right? We know that from just our very elementary algebra. So multiplying a row by a non-zero constant shouldn't change any of my solutions, x, y, and z. And adding a multiple of a row to another row, well, Back in high school, we all learned that to solve a system like this, we could just add them all together, couldn't we? So if multiplying doesn't change the solutions, if adding two equations in the system doesn't change the solutions, then doing the same thing in our augmented matrix is not going to change the solutions. So let's use our elementary row operations then to solve a matrix. I'm going to make this matrix a little bit different than the one that we had before. The reason being the one we had before didn't have a solution, and we're not going to cover that in this video, that case. But let's say I have this matrix given this way. It's very similar to what we had on that first page. So really all I think I've changed is maybe this value right here and these values here. Anyway. So this is my new matrix. Now I want to solve this matrix, and when I say solve the matrix, the general goal is that I want to eliminate everything from the matrix on this left hand side except for one entry in each column. Everything else in each column I want to be 0. And in particular, the one entry in each column should lie on the main diagonal. That's the best case scenario, right? So I want to try to set up the matrix in a way that I can use elementary row operations to get just a single entry on the main diagonal, and ideally I'd like to get it so that I only have ones. So I just have ones on the main diagonal and zeros everywhere else. Right? So let's take a shot at this. The first thing I'm going to do is I'm going to change row 3 and row 1. The reason is I really like this 1 right here. I want this 1 to be in the very top left of my matrix. Now I'm using this to describe the action, but this little kind of tilde mark, this squiggly line, this means similar to. And with matrices, we say similar to mean that it has the same set of solutions as the previous augmented matrix. So all I'm doing here is I'm switching these two rows. So I'm going to have 1, -1, 4, 10 on the top row. My second row, I'm just going to leave it there, 0, -2, 4, 6. And my bottom row is now 2, 4, -3, 4. Now I want to start eliminating values. So what I'm going to do first is I want to get my column so that there's only one entry in my column. I've already chosen this 1 to be the entry that I want, so I'm going to use this 1 to eliminate this 2. And how I'm going to do that is I'm going to use elementary row operation 3. I'm going to multiply this top row by -2 and add it to the bottom. Now you'll notice I'm not actually going to change my top row. I'm not multiplying it by -2. I'm adding a multiple of my top row to my bottom row, like we talked about in elementary row operation number 3. So with this action, my first two rows are going to remain the same. No changes. All right, I still have 0, -2, 4, 6 for my second row. But my bottom row is now different. I've multiplied my top row by -2 and added it to my bottom row. So 1 times -2 is -2, plus 2 is 0. So now this first entry is 0 in my bottom row. -1 times -2 is 2, so that's going to give me a 6 here when I add that 2 to 4. And 4 times -2 is -8, so plus -3 gives me a -11. And I need to do it in this last column as well after the line. So 10 times -2 is -20, plus 4 is a -16. Okay, so it looks a little bit messy, but we've gotten this first column done, so that's good. Now I want to work on the other two columns. So the first thing I want to do here is I actually want to make this middle row a little bit easier to use. The way I'm going to do that is I'm going to multiply this middle row by 1/2. Right, multiplying that middle row by 1/2 isn't going to change my top or bottom rows. I'll try to get this here fairly quickly. But the middle row now, I've just multiplied everything through by 1/2. Remember, this is elementary row operation 2 that we talked about earlier. So this becomes -1, 2, 3, and my bottom row is still 0, 6, -11, -16. But now I can use this middle row. Remember, I want everything on the diagonal. I want the diagonal to be the only thing that's not 0. So I'm going to use this middle row to get rid of everything else in the center column. The way I'm going to do that is first I'm going to multiply my middle row by -1 and add it to my top row. And then I'm going to multiply my middle row by 6 and add it to my bottom row. That's going to get rid of this -1 here and this 6 here. I don't care what happens here next. We'll deal with that later. Okay. So this is going to be similar to My first column is unchanged. My middle row is unchanged. Now, multiplying my middle row by -1 and adding it to my top row is going to give me a 0 here. I'll have a -2 plus 4, which is just 2. And I'll have a -3 plus 10, which is 7. Now looking what happens on the bottom row, multiplying my middle row by 6, the -6 and 6 cancel, give me 0. I'll have a +12 and a -11, which gives me 1. And I'll have a, over here, I'll have a +18 and a -16, which gives me 2. So that's really good. We're almost done. Two last things I need to do now. The first thing is I'm going to use this bottom row to eliminate everything else in this last column. So I'm going to multiply it by -2, and I'm going to add it to the middle row and to the top row. So that's going to give me this new matrix here. I'll have 1, 0, 0, 0, -1, 0, 0, 0, 1. Right? I chose this -2 to eliminate this 2 and this 2. So now we just need to see what's in my last column. The 2 in the bottom row is unchanged. I multiplied this by -2, so I got a -4, added it to 3, gives me -1, and -4 added to 7 gives me 3. Now the last thing I'm going to do is, I said I wanted 1s on this diagonal, so I'm going to multiply this middle row by a -1. And that gives us this new system, 1, 0, 0, 0, 1, 0, 0, 0, 1, with now my solutions over here are 3, 1, 2. Now remember we said before about the augmented matrix, this is our x, this is our y, this is our z. So now that we're in this final form, we get the solution set, x equals 1, x equals 3. Right, from here x equals 3, y equals 1, and z equals 2. And that's going to be a solution to our original equations, which again were 2x plus 4y minus 3z equals 4. And then here I have a -2y plus 4z equals 6. And I have a x minus y plus 4z equals 10. So go ahead and plug in x equals 3, y equals 1, z equals 2 here, and on the left you'll always get 4, 6, and 10 for this system. Alright, that's it for solving these systems of equations, and like I said, we're going to be using this when we go into elementary number theory. So we'll see you over there.